Hi guys, I'd like to welcome you to our next lecture here. Remember, we're talking about counting. And last time we looked at the fundamental counting principle, where we said if you have multiple events that are going to occur and you want to figure out the total number of possible outcomes, then you look at the number of outcomes for each individual event and multiply those. That product is the number of ways all those events can occur. Today we're going to move into a discussion of arrangements. How many different orderings can we have if we have a set? So for example, maybe there's a race with 15 runners in it, and we want to know how many ways can people finish first, second, and third. That would be an example. So before we do that, we need to talk about a new mathematical concept, really more of a mechanism or an apparatus known as the factorial. So let's get started here. Come on, here we go. Head over to our notes. All right, so let's suppose that 4 runners are in a race. Let's call them runners A, B, C, and D. How many different finishing orders are possible? Well, we could do this like last time. We could just start a count, right? So let's think about this. We could have A, B, C, and D. We could have A, C, B, and D. We could have A, B, D, and C. A, D, B, and C. Then we could say A, how about A, C, D, B. And did we get them all? For A finishing first? Well, I think we might have one more. Let's see, 2 C's finishing. What about, we have A, B, D, C, A, B, C, D, C. How about A, D, C, B? And then we could play this game again, letting B go first, right? And so we could have B, A, C, D. We'd have B, A, D, C, B, C, A, D, B, C, D, A. And we could say B, D, A, C, B, D, C, A. We could do this again, letting C be first. You can kind of see that if we let C be first and then D be first, we'll have 4 of these, right? And each of these has, let's see, how many? 1, 2, 3, 4, 5, 6. So if I were to do these as well and then count, I'd have a total of 24. Okay. We could also look at this with the fundamental counting principle, right? If you think about events, you've got these 4 runners, and the first place runner, right? There are how many runners that could possibly get first place? Well, there are 4. After runners 1, after someone's gotten first place, how many runners are left for second? Well, there are 3. And that means once first and second are filled, there's now 2 runners left competing for third. And after 3 runners have finished, there's only 1 runner left competing for that last spot. And so 4 times 3 times 2 times 1, which is indeed 24, okay? Notice that I started listing, right? And if I'd finished this, that would have been called the sample space. But I wanted to avoid that. I started listing it and I said, gosh, this seems like a lot of work, a lot of drudgery. So I just reminded myself, oh yeah, the fundamental counting principle is at play. And if we did this for a race with 5 runners, well, think about what that does. There are now 5 places to finish. The first spot has 5 options, right? Any one of the 5 runners can finish first. But once a runner has finished first, there's now 4 options for second, 3 options, 2 options, and then someone's got to be last. How about that person? And again, we multiply these. And so 5 times 4 is 20, times 3 is 60, times 2 is 120. Oh gosh. What if we wanted to repeat for a race with, how about 10 runners. Well, yikes. That would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That seems like a very large number. And I'm actually going to go compute that real quick. Let's see here. What does that turn out to be? I know you can't see what I have going on here, but pulling up a little calculator. I'm not showing you on purpose because, well, I want you to do it the long way first. But let's see. 10. Three 6 2 8 8 0 0. 3 6 2 8 8 0 0. Okay. If you want to put this in the context of gambling, if you were to guess the finish of this race, places 1 through 10, the probability that you actually guess correctly would be 1 over that. Probably not. So what we've just discovered is this thing called the factorial. In factorial, the notation is N with an exclamation point. That doesn't mean N with gusto and great enthusiasm. It means N times N minus 1 times N minus 2 times N minus 3 and so on. So if I had something like, I don't know, 8 factorial, when I write 8 exclamation point or 8 factorial, that means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm not actually going to figure out what that equals, but that's what the factorial means. So let's try some. 4 factorial. Oops. Get rid of this. Hold on, guys. So 4 factorial. That's 4 times 3 times 2 times 1, which this one we can do in our heads, right? 12 times 2 times 1 is 24. We already saw that up there above. How about 7 factorial? Well, 7 factorial is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1, which let's see what we get. 5,040. Okay. So fairly self-explanatory. And to be honest, a lot of calculators, you might even find the factorial button on them. Usually it's a second function, but you'll see that exclamation point as one of your buttons. And so you would just literally type 7 and then an exclamation point, and it'll spit out 5,040. All right, well, let's look at some more. Let's evaluate some expressions here, kind of do some arithmetic with some of this. Some of these problems, it's just kind of like weightlifting or running intervals or something. It's just to train, not for its own end. But the other of these expressions you'll recognize later with some new formulas. So the first one, 5 factorial minus 3 factorial. Well, that's 5 times 4 times 3 times 2 times 1 minus 3 times 2 times 1. And so 5 factorial is going to be 20 times 3 is 60, times 2 is 120, times 1, and then minus 3 times 2 times 1, which is 6. So we get a grand total of 114. Okay. How about the next one? Well, 3, not 3 factorial, just 3 times, well, 4 factorial plus 3 factorial. So what do we get here? 4 factorial, again, is 24. And 3 factorial is 6. So 3 times 30, perhaps better known as 90. Okay. And how about C? 3 factorial times 7 minus 2 factorial. So 3 times 2 times 1 times, and then 7 minus 2 is 5, right? So 5 factorial. So this is going to be 6 times, and then we already found that up there, right? That's 120. And 6 times 120 is 720. Okay. All right. How about 8 factorial over 3 factorial? Well, something interesting here happens. So 8 factorial is this. And 3 factorial, of course, is that. Well, what do you notice? Within that 8 factorial, there's the 3 factorial, right? So those cancel. And we're left with 8 times 7 times 6 times 5 times 4. 6720. Okay. Now E, this is one that's going to start to look familiar in sections to come. So let's take a look at this. We have 12 factorial. Now to start, I'm not going to rewrite 12 factorial as 12 times 11 times 10. I'm not going to do that because my denominator, 12 minus 3 is 9 factorial. And remember what we just discovered. 12 factorial is 12 times 11 times 10 times, well, from 9 downward, isn't that just 9 factorial? And so again, those cancel. And we have 12 times 11 times 10. 1320. Okay. How about F? So here, we got 10 factorial over 4 factorial times 6. 6 factorial. 10 minus 4 is 6. And so again, I might do this 10 times 9 times 8 times 7. And then when I get to 6, right, I'm going to share with this factor in the denominator, so they cancel. And then I could do some more, oops, no one read. I could do some more reducing here. Right, 4 factorial is 4 times 3 times 2 times 1. So I could say, so notice what I'm going to do here. I'm going to pair things up, right? 4 times 2 is 8, right? 4 times 2 is 8. So I can cancel those. And then 3 goes into 9 3 times. So my numerator and well, my answer is going to just be 10 times 3 times 7. So 30 times 7. 210. Okay. All right. Ooh, how about the last one? Think about this for a second. Do I really want to do 100 times 99 times 98 times 97? You can go get a cup of coffee or something to drink. I'll probably still be going when you get back. Times 96 times all the way down to 1. And then figure out what 99 factorial is. All the way down to 1. No, I don't. And here's the deal. To be honest with you, your calculator won't even do that. It will overload. Watch this. I'll even show you. You probably, and you don't need to worry about having a calculator like this, but I'm just going to show you. This will do factorials. Error, overflow. Too big for the calculator to handle. And what's also interesting is that, watch what happens here. Error, overflow. What that tells me, the calculator is not very smart, because, as hopefully you've noticed, instead of doing all this, 100 factorial is 100 times 99 factorial. Those cancel, and you just have 100, okay? All right, so the purpose of that little mini lecture is just to get you used to this notion of the factorial, right? Where you take a number and multiply it by all its previous integers, like 5 factorial, 5 times 4 times 3 times 2 times 1. You want to get used to that notation. You want to get used to thinking about what it means and to work and used to working with them. So spend some time doing that, and we'll meet back for seeing how this applies to counting.